Right, in today's video we're going to be talking about question number 6 from the 2018 BC exam. I classify this as a type 10 problem because it's heavily based in sequences and series. And we start off with the Maclaurin series, and we're given the Maclaurin series for ln of 1 plus x. Remember, the Maclaurin series is just a Taylor series centered at 0. So if you wanted to note that here, the center is at a equals 0 or c equals 0. This is one of the ones that I've asked my class to memorize, so this should not be new news to them. But what we're going to do in part A is we're going to change this Maclaurin series into another Maclaurin series. And so what I'm going to do is do this in 2 steps. First, we're going to replace the x with x over 3. So our series goes to x over 3 minus x over 3 squared over 2 plus x over 3 to the third over 3 and then the general term, we still have the alternator, and then the x over 3 replaces the x. And we have that. So this is the expression for ln of 1 plus x over 3. Then we want to multiply this expression by x. So we can take the entirety of this expression and multiply this all by x to get the desired expression. So f of x is equal to x times x over 3 would be x squared over 3. X times x squared would give us x to the third over 2 times 3 squared. That 3 squared is right there, the 2 is there. And then x to the third times x would be x to the fourth over 3 times 3 to the third. This 3 is that one. This 3 is that one to the third power. X to the fifth, there's 4 of them there and a 5th one there, over 4 times 3 to the 4th plus dot dot dot. And what we can see is our nth term is going to be x. This is our first term, second term, third term, fourth term. So our nth term is going to be x to the n plus 1th. This is our first term, second, third, fourth. So we see that 2, 3, 4. So what we have is n times, and then if you'll notice, we also have 4, 3, 2, 1. So we have this 3 to the nth power in the denominator. And then finally, we have the alternating, so we have to include an alternator. And there's our general term. Okay. This is worth 2 points. The first point comes from having the general term, and the second point comes from having the first 4 terms. So if you have the first 4 terms, you'll get +1, and then if you have the general term, you'll get your second point. Boy, that yellow doesn't read very well. Moving on to part B. Part B asks us to determine the interval of convergence for this series that we found here. And so oftentimes in class, the approach that we take for the interval of convergence relies on the ratio test. I honestly think that might be the best approach in this problem, so let's move ahead with the ratio test. And I'm going to go ahead and rewrite the general rule. just so that we have it for reference. So this is our general rule for f of x, and if we're going to do the ratio test on this, the ratio test says that the limit as n goes to infinity of the n plus 1th term over the nth term, if that is less than 1, then the series converges. So let's set up that ratio. The limit as n goes to infinity of the n plus 1th term divided by the nth term. Now, when we divide by the nth term, that is the same as multiplying by the reciprocal of the nth term. So this is writing it all out. We replace all n's with n plus 1 for the n plus 1th term, and then multiply by the reciprocal of the nth term to account for that division. If we start simplifying this expression, we know that the absolute value of a positive or negative 1 will go away. It cancels. So then I go to my next piece. I have x to the n plus 2 over x to the n plus 1. This gives me n plus 2 over n plus 1 gives you n just to the first power in the numerator. The next piece in the numerator we'll say is n, and then 3 to the n over 3 to the n plus 1 leaves a 3 in the denominator. I'm going to go ahead and get rid of that multiply symbol. So simplifying that out, we should have x over 3 and n over n plus 1. If we were to gather the n pieces together, we know that the limit as n goes to infinity for this is 1, because these are polynomials of first degree. Leading coefficients are 1, so that limit equals 1, and we get this expression as equaling to x over 3. So from there we can determine the radius of convergence by saying, in order for this function to be convergent, the limit expression has to be less than 1, which translates to the absolute value of x has to be less than 3 if you multiply both sides by 3. So we now know the radius of convergence is 3. This was a Maclaurin series centered at 0. So to determine the interval of convergence, we're going to need to test both sides. So in theory, we have from -3 to +3, and we're testing whether or not to close that interval. So we're going to test each one of those. So if we test the endpoint x equals -3, and if we test the endpoint x equals 3, that will tell us whether those endpoints allow for convergence. So we're going to stick -3 into the original function, or the original series expression, and see if we arrive at a convergent series. Okay, so off camera I wrote down the math process that I went through to simplify this expression. First I broke the -3 into -1 times +3. That exponent remained. And then we see that what we have is this expression times itself will always equal +1. And then 3 to the n plus 1 over 3 to the n leaves just a 3 to the first in the numerator, and the n is untouched. And so what we have here is a harmonic series multiplied by 3. So harmonic series we know are divergent. You can say divergent harmonic series, or p equals 1, divergent by the p-series test. So what's important is that we know that it's divergent, so our interval of convergence now has a open parenthesis on the left side, and we need to test the right side. So the right side is a little bit easier to test. +3. And in the process of simplifying this, we get an alternator that does not go away, and then a 3 hangs around in the numerator and an n in the denominator. So what we have is a alternating harmonic series, though I wouldn't call it that. I would actually run a different test on this. The alternator tells me a good test to run would be the alternating series test. So this is divergent by the alternating series test. An alternator exists, and the remaining piece is ever approaching 0. So, sorry, not divergent. I said that wrong. I apologize. Convergent by the alternating series test. So this converges. Okay. So by this approach, there's 5 points, and the first point comes from setting up the ratio. Let's pull that paper down. The second point comes from setting up and computing the limit of that ratio. So we went through this process of computing the limit of the ratio and arriving at the absolute value of x over 3 would be your next point. Your third point comes from recognizing then that the radius is 3. Your fourth point comes from considering both endpoints. So I'm not entirely clear on what it means by considering the endpoints, but I've identified that I've got 2 different endpoints here centered at 0. I believe that's the consideration that they're looking for, because the fifth point comes from the analysis, which is all of this, and the interval of convergence. So all of the analysis that leads to the interval of convergence is your fifth point. Moving on to part C. Part C says let P sub 4 be the 4th degree Taylor polynomial for f about x equals 0. So if we look at our polynomial, the 4th degree Taylor polynomial would be these first 3 terms. Use the alternating series error bound to find an upper bound for this expression here, the absolute value of P sub 4 of 2 minus f of 2. Okay. So what we're going to do is we're going to take this expression, which is a measure of the error, and we know that the error at a maximum is going to be the absolute value of the next term in the alternating series test. So we know the value of this is going to be less than the absolute value of the next term in the series evaluated at 2. So negative 2 to the 5th over 4 times 3 to the 4th. And then we need to evaluate this expression. Negative disappears with the absolute value. 2 to the 5th is 32 over 4 times 81. Which if we reduce that, we get 8/81ths. So the upper bound for the error of the 4th degree Taylor polynomial, centered at 0, is 8/81ths. So if we take this function and evaluate it at 2, we are going to be within 8/81ths of the value of the infinite series. This is worth 2 points. One point for using the 5th degree term as your error bound. So recognizing that the 5th degree term is what we need to use to calculate the error bound. And then the second point comes from coming up with that answer of 8/81ths. All right, thanks for watching. Be sure to comment, like, subscribe, and have a good day.